Hello, everybody. Welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities.
And every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us the keynote presentation.
And this week, we have a very special session with two speakers doing some amazing interdisciplinary work, touching on our theme, geometry. Our opener, Mohamed, is going to talk about unlocking new geometry for efficient structures, and our headliner, Timea Tihanyi, a great artist and a ceramist, is going to talk about making and breaking rules with clay and code, and the mathematical thinking that comes along with her work. So if you have any questions, please leave comments in the YouTube chat or our Discord channel. And it is my pleasure to introduce our opener, Mohamed Ismail. He is a PhD student in building technology at MIT and also a 2020 Paul and Daisy Soros Fellow. At MIT, Mohamed works with Professor Kaylin Mueller, who was also once a speaker at our colloquium, if you remember, and the Digital Structures Lab to design structural components that are cost-efficient and energy efficient for housing in developing regions. He has a diverse background with rigorous training in both civil engineering and architecture. And his research currently looks into the potential for structural and material optimization to improve housing insecurity situation in the global south. And this subject is particularly exciting to Mohamed and also other people in the field like us, as the computational tools and resources in structural design are becoming more and more available to solve real problems that's present in our built environment. Okay, without further ado, I'm going to give the stage to Mohamed.
All right, I hope everyone can hear me. Hello, everybody. Mohamed Ismail, PhD at MIT. Thank you. Got some thumbs up. It's a pleasure to be here. It's an honor to be opening for Timea. I will try my best to stay on time, and I look forward to the conversation we might have later on. I have a background in structural engineering and architecture, as was mentioned earlier on, but I wanted to share a little bit more about my background. This is a photo I took while visiting Khartoum, Sudan, a region that my family is from, and I always was kind of struck at how odd this comparison is. What you see in the front is something we call a zir, which is a clay pot that has been used for centuries in order to passively cool water that is publicly accessible to anybody walking by. So if you see these pots, you're always, it's expected that you would take a sip. And in the background, what we have is another common site in Sudan, which is a concrete frame building with brick inner fill, and it's incomplete. To me, these buildings always kind of reflected this interesting dynamic of the desires for dignified architecture, yet the cost was so extravagant and outside of the means of most people living in this context that oftentimes it was not impossible to see them unfinished. So to me, they always felt a little bit like unfinished dreams. And so with my background in architecture and engineering, I always wanted to find a way to affect regions that I was familiar with and have an immediate and profound impact. So a lot of my work is motivated by this question. This is especially important when we're talking about the challenges of scale for growing populations. This is a map of the most populous megacities over the next 80 years. And what you see is something that we're probably all familiar with, that by 2050, 90% of urban population growth is expected to occur in Asia and Africa. So regions that have very similar economic issues and situations, like my homeland of Khartoum, Sudan. This is both a academic and deeply personal interest of mine, because while I am from Sudan, I was born in California and I was raised in the Philippines. And all three of those regions show up on this map at some point. Now, my first venture into this started with a Master's of Architecture, where I had a thesis project motivated by this image, which is a photo of my dad's house that he spent about 16 years trying to build. Even as an expat with more means than most in Sudan, it took him a long time to build it because it was using imported materials, structural systems that were a little bit difficult and challenging to build in this situation. And so I proposed a typology that used materials and structural systems that reflect the mechanics of those materials, but also was cognizant of the culture of Sudanese housing. Can it be arranged in a way that you have the public-private gradient, the separation of genders, and still call it something that is Sudanese, even if it doesn't look like what most people are building? That Same interest led me to my PhD research, which Zihan was very kind to introduce earlier on, which is basically the optimization design of concrete structural floor systems. And in my PhD, if you just wanted to jump to the end of what I've been up to, I've developed a shaped optimization method that can reduce the embodied carbon and mass of residential floor systems by over 60%. And we're talking about multi-story concrete brick frame buildings that are going up in less economically developed countries like Sudan, India, et cetera. Some of you may be familiar with the embodied carbon aspect, that this is the carbon that's associated with the material extraction, material processing, material construction and deconstruction. And you might know that the construction sector contributes to 11% of global carbon emissions. Most of that is due to concrete construction. So 8% of our global emissions are due to cement. But what's really interesting is if we revisit the issue of global urban growth, we see that the expectation of our already outsized use of concrete is that it'll grow, especially in developing regions. So on the right, we have a plot of predicted cement production, which is expected to double by 2050, especially in regions like Africa and South Asia. And what I want to point out is that because of this growth, building-related emissions, just like the impacts of climate change, are not shared equally. In developing countries, construction can contribute 2 to 3 times as much as they do on average across the world. So with the ongoing climate crisis and the sensitivity of these regions to climate change, this does require an immediate response. Now, in response, I focus on floor slabs, which might seem somewhat pedestrian and uninteresting, but they actually occupy a lot of space and mass in construction, especially because most of our floor systems are deployed using materially inefficient practices. This is an informal survey of housing construction that was being done in India when I started my research. And you can see that most of these structures are being built using prismatic beams and slabs, rectangular prisms. In fact, they make up at least 50% of the mass and embodied carbon of a building structural system, and it actually goes up the taller a building gets, which is becoming more and more the case. To illustrate some of the arguments that I make with my research, here's a diagram of a one-way concrete floor slab that spans across 2 beams that are about 5 meters apart. In an MEDC, or a more economically developed country like the United States, which is where I reside, we build a lot with flat slabs. And that's because material costs are low, so we're not too worried about inefficiency, and labor costs, this keeps labor costs low, even though our carbon emissions associated with this type of construction is relatively high. So if we were to propose a shaped slab system like this that was developed using an algorithm that I developed, labor cost goes up and it becomes far less feasible to build something like this, even though we can argue that the carbon emissions are substantially lower. Whereas in less economically developed countries, we still build using flat slabs, even though material costs are so much higher than they are in countries like the United States. And labor costs are low. Regardless. And so the carbon emissions remain high. And so if we were to propose a shaped slab system, labor costs might go up a little bit, which actually might be a good thing. We're shifting the cost for materials to human well-being and lifestyle and livelihood, while reducing material costs and reducing our carbon emissions simultaneously. And this is really all enabled because of the cost breakdown of residential construction. In the United States, we're about 50-50 between labor and materials. But in places like India, materials can account for over 80% of residential construction costs. So why are we still building using these materially inefficient methods that were developed to reduce labor rather than material? And I argue through the research that geometric complexity offers an opportunity for material efficiency. This is not a new idea. This is, we have a lot of industrial prototypes that have showcased how you can remove material through some efficiency to a certain extent. But these are systems like waffle decks, bobble decks, hollow core slabs. They require infrastructure and they require a huge investment in capital for countries. So places like India, once again, where I spent a lot of my time, this is not totally feasible. They're slowly gaining traction, but there's a lot of investment up front that needs to be done to make these happen. In academia, there's a lot of really exciting, beautiful examples of materially efficient systems that have been developed by some of our colleagues, but they often are done using digital fabrication methods that are not available or materials that are not actually allowed by code or not standardized to a certain extent. So these are systems that might gain traction within a few decades, but not immediately accessible. And so in response, I'm trying to do something in between. Can we do something that pushes the accessible technology and standard materials, but is still reasonable for construction in the next 5 to 10 years? And I focus most of my research on residential scale construction because that's where most of the concrete for building use is expected to go. And ultimately trying to reduce environmental and economic costs without increasing the complexity of fabrication too much beyond what is possible. The shape optimization method looks like this. We have a separation from we basically define geometry, analyze that geometry, and then run a constrained optimization. And the separation of the analysis and the design of the geometry allows for a lot of flexibility, but this is what that shape optimization method looks like. And we were lucky enough to have an opportunity to build several examples of this. One of our biggest ones was a 15-foot beam in New Delhi, India, with our partners Tara, who built it and also tested it in a government lab to verify that it behaved the way we wanted. It met Indian standards and was still 50% less embodied energy when compared to a standard floor slab. And it just did very subtle shaping, built using a formwork material like steel plates that were regularly used in India nonetheless, and was substantially cheaper when you look at the actual total materials. Now we're really excited. We're getting to look at other regions. This is a proposal that we're developing in Mexico City with partners to basically make subtle changes to a system that they already use that's both precast and cast in place. I've also been thinking a lot more about how this research can go beyond the lab. Can we actually engage other people, and that means making these methods accessible. So I've developed a plugin for the analysis and design of complicated concrete structures, which means that we can pair this with things like virtual reality and machine learning in order to have predictive models so that someone who doesn't fully understand how concrete mechanics works can still mess around with the design and optimization of these spaces and understand the implications of all of their design choices early on in the process. So how can we actually include the end user in our low carbon design processes? It's also allowed me to take my method of structural optimization and bring in other partners who can talk about performance metrics outside of structural behavior, like thermal behavior, acoustic behavior. This is work I could not explain, but a partner in Penn State has done amazing work trying to figure out how you can optimize for both sound insulation and structural efficiency. Or can you do lifespan operational energy where you're actually using it to store, you're using shaped concrete slabs to store thermal energy and heat and cool a building passively throughout its lifetime, where in a place like Cairo, you could actually reduce the total energy of a 50-year lifespan for the building by 60% just by shaping your concrete floor systems. So to summarize, some of the lessons that I've learned in my research is that sustainable construction needs to question our most common practices. I think that's kind of an obvious question to a lot of us. Holistic design has to occur across various performance metrics, which include space and aesthetics and human well-being. And we need to be able to work where we can have the greatest immediate impact. And for me, that's been a lot of the developing world, but really low cost and low carbon solutions are needed worldwide, which is extremely important when we think about how there's a vast difference between climate responsibility and climate vulnerability. It's almost the inversion. And there's a wide gap between those who need help and those who get it, even in our own neighborhoods. So I think it's both in our best interest and frankly, a moral imperative to respond to the needs of the majority through innovative design and technology. And with that, I will stop talking. Thank you so much for having me once again. I look forward to hearing Timea's talk and the discussion we have later on.
Thank you for the great talk, and we'll proceed to the talk of our headliner and have a joint Q&A session at the end. And now I introduce our headliner, Timea Tihanyi. She was born in Hungary and currently working as an interdisciplinary visual artist and ceramist in Seattle, Washington. And she holds a Doctor of Medicine degree from Semmelweis University in Budapest, Hungary, and the Bachelor of Fine Arts degree in ceramics from the Massachusetts College of Art in Boston, and also a Master of Fine Art in ceramics from the University of Washington. She currently teaches in interdisciplinary visual arts department at the University of Washington and also runs a techno-ceramics research and mentoring space called Sleep Rabbit in Seattle. And she currently also has an exhibition called Object Permanence on view until May 29, 2022 at the Bellevue Arts Museum in Washington. So if any of you are in the audience are around that area, you should go check it out after today's talk. And without more delay, I will let Timea tell us about her interdisciplinary journey in art, coding, and math.
Thank you, Selena, for the nice introduction. And thank you, Mohamed. That was an amazing talk. I really enjoyed it. And I'm going to turn on my presentation and get it full screen. So I I was very surprised getting this invitation to the colloquium, and I feel a little bit like an interloper here as always, but in kind of like in technology and in engineering and science roles. I am a visual artist. That's the first and foremost to know about me and my practice, but I do work with ceramic 3D printing and applications of mathematics, design principles, and some even like architectural applications. So hopefully I can show you some ideas today that will be interesting and can also be implemented in some of the work that you guys are doing. But I wanted to start out with some student work of mine, because I teach in an interdisciplinary visual arts program. I right now teach a lot of classes that have to do with craft and technology, the relationship of the two, as well as art and mathematics. This is a student work, a graduating student work that at the time had nothing to do with math, but I think today you're gonna see like how it stayed on my mind and influenced the work. But the ingenuity of students is amazing and becomes a continuous inspiration. So this particular student took hundreds and hundreds of Rubik's cubes and created an animation of the moon landing with that. And I think I might have a little bit of a delay with the loading. Yes. So instead of just kind of like changing the stickers, the color stickers on the in the little squares, she actually solved every single Rubik cube for creating the right part of the pixelated matrix of the moon landing and presented it as a video in her exhibition. I think now I'm having a little bit of a difficulty, so maybe I'm wondering if you guys wanted to share from your end, or should we keep going? Okay, so maybe we'll just keep going. So I've taught two different iterations of an art and mathematics course, and then the first iteration, that was maybe like 10 years ago, we were working a lot with the very typical stuff in an art and math context, so like symmetries, and the students were actually manipulating materials, learning to craft objects with them. These were made out of plastic bags, using the ideas of symmetry. And in a newer iteration of the same art and math class, we were using digital technology, starting out with a cyanotype, and then using Photoshop to replace colors and manipulate the image and tile it in a wallpaper style. And then the students are bringing their own wallpapers into the classroom, and we are putting them together into this large quilt. I do seem to have a little bit of delay, so my apologies. Another aspect of the art and math class that we all enjoyed was a Buckminster Fuller geodesic dome project that the students were building out of cardboard and tape, and really had to understand how structure and some ideas of tension and compression worked. We also use in the classroom, and this is not an art and math class, this is just a regular making class in sculpture. We also use ideas of topology. So here the students are putting on t-shirts and stretching them out with the internal structures, and really creating ideas of shape and volume with transforming the shirt itself. Another kind of type of project that we often do in sculpture classes is topographical representation of objects, and I've been teaching for 20 years, so this was one of the early projects that we were doing in a sculpture class. And at that time, I wasn't thinking of 3D printing, but of course now, like conceiving how an object would be built up from layers, individual layers, and what the outline of those layers might be. That is the kind of thinking that this project practices. So in a more recent class, which is called Maker Practices, Maker Cultures, we are using various methods of fabrication, so laser cutters and 3D printers, to do similar projects. And I really love the way the students are kind of creating the shape, creating the volume by slicing things and joining things differently. And then lastly, this is the last batch of student projects I wanted to show you, because this actually brings us to my work. In the most recent iteration of the art and math class, we were working a lot with iterations and algorithms, and the students, besides learning the technique of a Salish, post-Salish weaving, which is traditional to our Pacific Northwest, they were also asked to come up with various rules. This binary pattern can be changed and can generate a pattern. And you will see later how this actually shapes my own work. So besides the university, I also run a 3D printing studio that specifically focuses on ceramics, and this is Slip Rabbit. The studio's goal is mentoring and research in the area of clay printing, really seeing where the clay printing can be expanded into interdisciplinary, cross-disciplinary areas, and how it can be used and how it can be pushed further. So the studio has been working, has had the first students come in 2017, and we have internships, collaborations, and residencies. And we'll see some of those examples of the works with the students later. But my background is in medicine, and my interests is still in this world between science and art, between sort of perception and abstraction, between the various ways the material world incorporates aspect of like an abstracted scientific world. So I wanted to show you an example of a work that I did with 3D printed ceramics, but it really kind of goes back to some older kind of interests of mine between how materials relate to one another. And I had a good fortune to have a residency at the Glass Museum here in Tacoma. And for the residency, I printed these ceramic vessels. These are printed in porcelain, and some of them I fired, and others I actually just took molds of, and the molds were going to the Glass Museum that had an active glass blowing workshop, and we worked with the gaffers to blow glass into it. So as the result, I had two pieces. One of them was in glass and the other one was in ceramic, and the two came out of the exact same form. So the form that I designed on the computer, that I printed, took mold of, it was forming both of these objects, but the objects really shaped as a result of the specific process that works that particular material. They were really shaped differently, and I really enjoyed the tension and the combination of that. My artwork is, I would say, like probably half and half in nature, between thinking about the process, the technology, the abstraction, and really thinking about the physical experience, the bodily experience, kind of like an emotional experience. So you might see that coming back in the most recent work, and I will show you some more technical projects next. But I wanted to, hopefully this video is going to run. I wanted to show you this video. which is a participatory project we often perform in the studio with visitors. And you are going to see my ceramic printer, which is a Potter bot. This has the tube set right above the nozzle. The tube is filled with maybe like cream cheese consistency, porcelain, clay, unfired. This is a continuous extrusion. And the machine is not super sophisticated, but very, very reliable. And what happens here in this particular project, that the participant acts as the building platform. In fact, the form that's being printed is a sphere. So it could not print. It would not make sense. It could not stand without the hand of the participant. So there is a collaboration, there is this kind of continuous dialogue, there's a dance between the hand and the person making it and the machine. And I really offer this as kind of like a symbolism, a metaphor for the rest of the talk. So I'm just gonna skip ahead and show you a project that is not mine in origin. This is Henry Sagerman's work of the 5-cell beach ball cube, which is showing like the 4-dimensional representation of a 3-dimensional object. And I've worked on a math art project with another mathematician, from my colleague from University of Washington, Jared Evetria, where we interviewed various math people about the research that they were doing. That's how I met with Henry. And I was really interested in his way of conceiving an abstract idea, which would be like a 4-dimensional object, and using the 2-dimensional representation, using the shadow, using this projection as a way of allowing us to visualize it. So I asked Henry for the model, and he created this on actually, I don't know the software, but he created this and printed it out very small. And what I wanted to do a really large porcelain version of it. And for that, I needed a ceramic 3D printer, and I used a powder printer basically to make the different modules that make up the form. Now there's a little bit of a delay here on my end. Yes, so the parts were cast, I built them together, and then kind of the physical reality of ceramics took over. In the firing, everything kind of moved and changed and slumped. So I ended up with pieces that were very perfect representations, and then pieces that were a lot more imperfect representations. And this went into a final installation that showed both the Rhino structure of it and the actual objects. So just maybe a little bit about 3D printing, because I don't want to assume that everybody's equally familiar with that. And it will have to do with some of the later projects that I would like to talk about. Basically, the process of 3D printing, there is a form giving process for most purposes. For many people, this is some kind of CAD. And then there is a translation process that is done in a slicer program, translating the geometry of the object into a machine code. And there is the prototyping process, so the actual printing. I use Rhino a lot, and I kind of use it in very low-tech way by creating volumes of various sorts. So here you can see an example of a vessel, actually a family of vessels that are made of tori and cylinders and truncated cones, just stacked together in various ways. And each will give me a different shape. Then the translation happens with the slicer, and then the printing happens with the Potter bot. And from very early on, when I started working with 3D printing, one of the most interesting aspects of the ceramic printing became the point when the printer, the nozzle, leaves the perimeter of the object. There is a drop, there is a loop that happens, and it really is only dependent on the size of the extrusion. So the first objects that I have created, and this was 2017, not very many people were 3D printing with ceramics at the time. There was no formal kind of like literature and follow, like guide to follow at that point. We were kind of experimenting with the students and seeing what happened. So the loops happened. And very soon, it became the most interesting thing to me to kind of try to pattern these loops in regular fashions and also in irregular fashions, and then see the kind of textures that could develop with that. So the way in the studio that we work with the students is that every student comes from a different background. We have a lot of people from engineering, computer science, mathematics, art and design, architecture sometimes, and they have their specific interests, what they would like to do. We usually develop a workflow. I conceptualize a project, and then the students kind of build it, and all this information kind of flows in and out of the studio, like allowing other people to also use some of the research findings. So with the loops, one can go like super extreme in size, and these become almost like these wing-like structures that would literally be like 5 centimeters, 2 inches long, and would have to be resting on a support, usually my hand, in order to hold up. Many of the things that we have found during these years were the results of accidents. With clay printing, things are never as predictable as with regular printing. It never is a goal. We're not trying to prototype something with the exactness of what's visible on the screen. So for example, on the right, on this pink pot, there are these palm leaf shapes. These are tapered, basically half circles, half rings, that just happen to print that way because of the nature of the clay. Other times pieces might fall apart. With ceramics, that's never a problem. It can always be built back together, like the vessel on the left, the gold one, and become a completely new thing. On this image, you see 2 different prints of the same file. So on the left is where the layer height is gauged to be kind of like, normal. And then in the middle, the layer height is set at maybe at the double of that. So it's kind of extreme. The extrusions don't stick together. And the most interesting thing is when these start falling apart and crumbling, and we can sort of save that all in one. So I mentioned that I work a lot in Rhino. Another way to work is to work with meshes, which I don't tend to do as often, but for this particular project, we did use meshes because we were going off of rock formations and stones, found stones, and worked with the meshes quite a lot. Another reason why I work with a mesh often is now we have 3D scanning capacity at the studio, so there is a lot of mesh fixing that's going on for us. A third way that I work, many people working with 3D printing work now, is Rhino with Grasshopper, so using parametric design. And this is a collaboration that I'm showing here with a mathematician, Frank Ferris, on algebraic knits. And these are using the Fourier series to create the loops that will weave in and out under and over one another and create these knitting kind of textures. And here you see the second printer in the studio. This is a WASP 4100. It's a much bigger machine, a much more sophisticated machine. It's a Delta printer where the three arms move up and down on the belts. And this is able to stop the extrusion, retract, move to somewhere else, and continue. Here you see the exact same object printed in porcelain on a scale of 45 centimeters and on the scale of 5 centimeters. So there's quite a difference in the resolution and how everything works, or it doesn't. The things that are becoming more fascinating to me recently are sort of hacking the G code, editing the G code, doing things with the G code. So I'm going to show you a project that I worked with a designer, a colleague of mine, Audrey Desjardins. And we call this project the listening cups because we are using sound information from various environments. Some sounds are really loud, some sounds are very varied, and kind of using the G code of the cup as it would be without anything. And because neither of us know really how to code, we were using it just as an Excel table and combining it with the sound data. Basically, what's happening is where there is sound data, we are taking into account the amplitude of the sound and then translating that into a duration of pause on the printer, which was a very simple technique, but gave us these bumps that corresponded to the sound volume. So using that same idea, but maybe a little bit more of a math and the Python code by one of our students, I was sort of revisualizing the sound detouring the printer, the nozzle, by choosing one out of the 4 possible alternative locations. So basically we decided to make the sound, create sound ranges, and each range corresponded to one of the 4 possible new directions, and it would send the printer into those directions as it encountered the coordinate point. And these are the resulting vessels. So in neither of these pieces, the form is actually the result of the sound. The texture is the result of the sound. The form existed, it was translated into a G code, and the sound was added as sort of a texturizing element. And this, the most recent collaboration with Audrey Desjardins is this project that we call the Inner Ear. We are working on it with a bunch of students, forming a research group. And this is a smart porcelain object that will collect vibrations. And the vibrations are both translated into a light that gives the user the feedback about the system is being on and collecting, and also will create these cylindrical shapes as replaceable onto the object. So the user will give us their data, we will print it onto the cylinders, and then we'll return it to the user who will keep using it in their home. So I would like to show some mathematical projects, and I will talk about the most recent exhibition. And the math projects really kind of all could be collected under this idea of iterations. I became very interested in using very simple rules for creating complex systems. And when I went to talk to mathematicians about it, they recommended that I would look into the elementary cellular automaton. Stephen Wolfram did a great job classifying them and writing a lot about them. So I'm not going to attempt to do the same, but for those who may not be familiar with that, in an elementary cellular automaton, there are two possible states, 0 and 1, black or white, yes or no. And the state of the cell and its two neighboring cells would be determining the new generation below, like the state of the cells in the new generation below. So there is a translator that will run along the lines of this code, basically white, 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 black, white, 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 white. And in the new row, it will use the code on the right to translate it to the color, the states of the cells. So I was very interested in making this patterning tactile. Here is the vessel that I created with that. And in Rhino, this is really just a combination of a large cylinder and a whole bunch of little blocks that are stacked together. And this is what it looks like on the printer. So kind of like figuring out a method for this and figuring out a method for printing, that's one of my interests. But in the case of the cellular automaton and a lot of these iterative processes, the kind of what happens, how can you reg the system, what are the rules that are necessary, how additional rules might change what happens with the pattern, are also of great interest to mine. So here is the rule 105 in the elementary cellular automaton, and here's rule 105 with an extraneous rule added to it, which actually, and this work was done in 2018, puts viruses in the matrix, and the viruses kind of start a whole different patterning process below them, and kind of creating a bit of a disarray as more and more generations happen. Here is the same thing printed. And that work led to another research collaboration. This time, this was a math research group of math PhD students and undergraduates. And we were working with another type of creating complexity. And these are the Senpai Models, chip firing games. So these are amazingly complex patterning systems that you might imagine as having a gridded game board into which sand is being poured. The rules have to do with when, what is the state of saturation, how many grains could each cell hold, and when is it going to start spilling it into the neighboring cells. And the colors in the animation, they were representing just the number of sand grains, and how we were curious of how it changes and whether we can see a pattern in that. So there was a mathematical research there that I participated in, and there was also, again, making the difference, making the change of the rules tactile, and by that tactility, it becomes more visible of what's happening with the mathematical model. Okay, that leads me to the very last thing that I wanted to show you, and this is the work with embroidery patterns. In Hungary, where I'm from and where I am right now, the embroidery has a huge importance, a big cultural history. It's also very politicized. There is symbolism in the embroidery, and I'm talking about cross stitch, which is also based on a lattice. That is also very politicized. And I'm happy to talk about that later. But what I'm doing here, I'm collecting these historic patterns. They are very simple, usually flower shapes, maybe star shapes, and I'm putting them into Rhino and starting to do these symmetry manipulations, transformations with them, and I get great complexity. And what's interesting is that in the complexity, there are new patterns that emerge. And I tend to think that this is kind of the way that generations and generations of textile artists would come up, or people working with tiling patterns, architectural tiles, would come up with sort of the newer innovations. You pick some rules, you start repeating them, you're seeing the pattern develop across the surface. For a while, I was printing them on cylinders because that lets me see the pattern better. But very soon, I started thinking of them as textiles and started manipulating the forms as they came off of the printer. So these scrunched together shapes are not printed like this. They are still printed as cylinders. And I really enjoy the idea of manipulating them, pushing them. And this may be Mohamed's, like down in Mohamed's alley here, about the way the pattern is on the form that's influencing largely how they can be scrunched together or how they will hold up. So this is the work in the exhibition, or Object Permanence, that's up at the Bobby Art Museum right now. These are about the textile patterns, but it's also about the way people hold these traditions, and kind of like the significance, the tactile significance of these fabric materials. You do actually see a lot of hands in the show. They were all 3D scans of my hands and 3D printed. And that's the entirety of the show, which I'm sharing with another ceramist, Sylvia Thur, who's doing those simple geometric shapes with that. And then this is one before the last slide, just wanting to show you very quickly the book I wrote about ceramic 3D printing and math, and some of the ideas about these interdisciplinary ways that the two are connected. And this is freely available as a download from our website. And I think my last slide is lagging, but I just wanted to thank everybody for being here and open it up for questions.
Thank you both for the great talks, and we will now start a joint Q&A session for both speakers. In the meantime, please continue to post questions in the YouTube chat, and if you still have questions left afterwards, please use our Discord channel for offline discussion. Okay, so I will start by first question posed to Mohamed. So in your slides, optimized beams you showed mostly have like low frequency variations, I guess partly due to the representation. We are curious that do you think there is a potential to use a 3D representation like a triangle mesh that has like more degree of freedom to like even optimize the microstructures within the beam and then 3D print the beams to make it better for your purpose?
Yeah, that's a great question. First off, amazing talk to me. It was a pleasure to see it. Thank you. So it's an interesting question. I obviously in the time couldn't really get into the details, but basically what I'm working with is analytical representations of concrete mechanical behavior. So it's a fairly complicated material system, and we have to make a lot of abstractions in order to get a analysis method that can go fast enough that optimization is 30 minutes per design. Basically, trying to figure out how fast we can make this. And so it doesn't get into the microstructure, it doesn't get into the surface structure, but theoretically, that's a whole realm of material optimization that I would love to get into, and just really haven't had the time in my short PhD. So I'm hoping, if you can think of anybody who can tell you what the performance, how the performance changes with surface structure and surface variation, then please let me know, because I would love to include that as an added layer of complexity. It's essentially, how do we remove material or put the material where it behaves best? And I think in the acoustic side, in the thermal side, those are both places where you can really benefit from increased surface area and where that surface area is located. But the analysis that I do is actually fairly simplistic. It's essentially doing hundreds of calculations that engineers regularly do by hand, except instantaneously. And so we're automating that process, but it's still a calculation that you could do by hand. It's not taking advantage of how intense or dense your mesh could get. And so my short answer is yes. And my long answer was that.
Okay, I see. Thank you for the answer. So do you think like the bottleneck is like in the speed in simulation in some sense?
Yeah, that's part of it. It comes down to the speed, but also how much of it is meaningful, because I could easily represent this in a more complicated triangular mesh, but is that going to tell me anything new about the behavior, or can I keep it at low resolution and still get, as you saw, I personally am really excited by the designs that we get from the spaces that we have, and it's a low resolution design. It's actually represented through NURBS, and the NURBS representation was actually part of how the optimization process was developed, because it allows us to interpolate between a couple of structural sections. So really, we're abstracting, but we're abstracting in more places than we normally do. When we do structural design, we usually choose the biggest case and design the entire structure for that biggest case, but loads are not distributed that way. They behave differently at different points in a structure. And so if we can respond a little bit more sensitively, you can do that. But to your question, there's obviously a further layer of resolution that I'm not getting into at all yet, but I would love to.
I see. Thank you for the detailed answer. Yeah, that sounds like a trade-off for like future researchers.
Yeah, or just
like model form.
Yeah, our computational tools get better, and we can do higher and higher resolution. But right now, there's a major trade-off in usability and time, and how much information you're getting out of that.
I see.
It's a great question.
Okay. Yeah, I'm gonna kind of ping pong questions across the two speakers. So next I have a question for Timea. So the loops you showed us in the ceramic work are like so beautiful. We're wondering, like, have you kind of thought about like further controlling the loop designs, by example, like designing the cross section of like the 3D printing nozzle, or even varying the nozzle a little bit to kind of have novel forms?
Yeah. I have thought about it, and kind of was very excited about pursuing the shaping of the nozzle for a while. But I think there are some, there is also that would be, I think would have to be in tandem with the material. And then the nature of this, that the extrusion needs to be super soft, the material needs to be super soft. So it kind of loses a little bit of the significance of what it's going to be extruding, like what is the cross section that it's going to be extruded through, because it won't really stack that way. But we have thought about that. One thing that's really interesting is that there is I think there is a way of like topologically thinking about the extruded clay, which seems to be the more interesting thing to me with the loops, that there is an outer radius and there is an inner radius of the same extrusion, and the form of the loop will really depend on that. So we have tried kind of going away from the perimeter with different shapes, but you mostly are getting loops because of the nature that with the extrusion rates and the kind of the path the clay is actually sort of making, that would just normally be a soft curve.
I see. That makes sense. Yeah. Seems like the materiality of clay will kind of limit the form.
It's really real, and it's really the thing that determines everything at the end.
Easy. Thank you for the answer. I guess that also kind of lead to my second question for Mohamed. So it's kind of lead to like this like connection between like form and manufacturability. And you kind of mentioned in your slides, like there's this trade-off between manufacturing cost and the material cost in your research. And I guess we might have missed it. Like how exactly like a new geometry form will increase the manufacturing cost? Or like more specifically, do you think is there like a way in current research to quantify manufacturability with geometry form in the optimization process?
Yeah, so maybe I misspoke there. The trade-off is not clear. If we build using traditional building practices the way they are today, which is largely manual formwork, manual construction where we go, complexity always increases the cost. But what we obviously, as Timea was demonstrating in her work, and we're seeing in a lot of our colleagues' works, is that digital fabrication opens up a whole realm of possibilities, because ultimately the cost of constructing a simple formwork versus more complicated formwork using a robotic arm is the same, in theory, if you're doing it correctly. And so what I have been really interested in is how we can come up with something that fills in the gap of knowledge between the digital fabrication and the actual design of structural elements, so that you can inform your design by the fabrication that you're planning on using. And so the India case study was one of our earliest examples of this, where we had assumed that we would do CNC routing and thought we could do it with foam. And that was because that was something we had done here, but we found that in India, you couldn't buy foam at the volumes that we needed because of land pollution policies. And so they were planning on milling it out of steel blocks, which is absurd and extremely costly. And when we found that out, we had a very quick conversation and said, we don't have to build it with doubly curved surfaces. We can change the design, the parameters, and how they're related to each other in order to do something that does work with what you do. And they told us steel plates, that's what they build with. And so if you take care of a steel plate mold, you can use it hundreds of times. And so quickly redesigned the slab within an hour and had a design that was very comparable to the original design, but now was all singly curved surfaces. And that kind of conversation is what we're having with every partner we work with now. It's, what is possible? Oftentimes people get very excited and say, we can build anything you say, but that's not what we want to hear. We want to know what you build with and how we can design according to the constraints of that fabrication method. And that, in my mind, is closer to reducing the cost of complexity and acknowledging that complexity can be informed. It doesn't have to just be a generic, random optimized form. It should be something that responds to what's possible.
I see. Thank you for the detailed answer. Yeah,
I love that comment, Mohamed. I'm sorry, Selena, to cut you off, but that really resonates with me and my experience in 3D printing with ceramics. It's like not every form lends itself to be 3D printed in clay, and sometimes that fabrication is the one that makes sense. And other times there's another way of fabricating that makes a lot more sense. So in the smart object of that vibration sensor that we are doing, the centerpiece is actually, we thought about that, we tried it, and it's not something that will be 3D printed because it's such an extreme curve that it would need support. So it just doesn't make sense. But we could do a prototype by CNC, we take a mold of that, and that would be slip cast, and everything else will be printed.
Yeah, and the amazing thing, like that's what was so exciting about the work you were talking about. Sorry, Zian, we're skipping a little bit. Is that kind of comes through conversation. It comes through communication with people who know better. I don't know everything about concrete construction, especially when I go from country to country. But if we're able to learn from what they're doing and have them look at our designs early on, we discover new opportunities on both sides, because we all come in with our assumptions of what is possible, and oftentimes you can find new solutions. So that's a perfect example of that happening.
Yeah, thank you both for the engaging discussion on this topic. But it's definitely very interesting because in our field, I think we comes up with all kinds of geometry forms, and we have very little knowledge about how to manufacture and also the material property that comes along in that process. So it's very interesting. to hear about those questions that we might have at this gap. And I guess that also kind of flows to my next question for Timea, is that, so like in your example, like we see kind of your art, which is physical, but we see it right now in like a digital screen. And so I guess like, why do you think it's important to actually build like a real world object in the end, you know, like, cause like right now we are appreciating this art through the screen, like we can even appreciate it during virtual reality. Like, I guess what's your thoughts on like having like a physical art piece?
Oh my gosh, yeah, I have lots of thoughts on that, maybe more than we have time. But I think there is I think as human beings, we are like our brains are still wired to understand things through our sense of touch, and that really has like also temperature sensor, pressure sensor, like it's very, very complex, and it kind of codes things in our brain. So even in virtual reality spaces, I do think, and this is not proven, so probably a researcher needs to look into that, but I do think that there are virtual sensations that evoke, like, you know, like they really facilitate the same brain area. So like we kind of like remember that those tactile things and the spatial things that we know from other areas. So I really wonder if somebody is just purely raised on virtual reality and they don't have any physical experience of any sort, not movement through space, not touching objects, then you know, what's their experience is like of that. So I feel like it's very important for us to have actual things in our physical experience, but it's also, I think, by actualizing something, by printing, really I always feel like I learn from the process, because it cannot be taken for guaranteed. The object that is printed is never the object that's on the screen. So there is a lot of chance for failure. There is a lot of chance for new ideas in the physicalization of things.
I see, thank you. Yeah, that kind of also goes to the next question. I guess like how easy it is to control the pattern in your ceramic printing. Like if we can simulate pattern, do you think it would be easy to design a ceramic card with like haptic information for even like visually impacted people for that purpose?
Yeah, I mean, I think that would be amazing future research of like what other ways could this pattern be applied and how to be controlled. I mean, I'm building it kind of like in a reverse engineered way, where I know exactly what my layer height is going to be, and then I calculate back and the diameter, and I'm really just calculating how big my dots need to be, and then putting everything into Rhino in a way that the, you know, the measurements and everything works out, so everything is exactly a unit, for example, right, with that particular nozzle, and then the whole thing is completely different if I use another nozzle. So I have a very rigid workflow process that I think works for the visual aesthetic of the pieces that I create. But I'm also very interested in what other ways could this be. Like, can the pattern be read by a camera, and then somehow like translating this through a completely different workflow.
That sounds amazing. Maybe we'll make another artwork based on that concept. So okay, next question is from Mohamed. So I guess when we like first think about architectural geometry, at least like from my side, I think about like the overall form of the architecture, like Sydney Opera or like even the MIT's data center building. So I guess you were kind of really focused on like a subunit that makes up an architecture. So do you think the future in like architecture geometry or like geometry optimization is like in optimizing building subunits, like the beams that you in your work, or like the entire building form?
Oh, that's a great question. I think the future is okay, so I say this somewhat naively, and also recognizing that it's also the past of architecture geometry, but we can't ignore performance when we're designing geometry anymore, especially, like I said, with the impending impacts of climate change and the role we play as designers of the built environment. Our decisions, as minimal as they might seem, like the thickness of a concrete slab, can have major ramifications when you're talking about a construction system that hasn't changed in 120 years. It has had ramifications and it continues to. And so to me, the sub-element focus is a really lovely way to look at it as an individual component that I can contribute, knowing that, if this were put into action, it can have an impact way beyond a singular building or a couple of buildings. It's really talking about the system itself that, like I said, has been in use and is ubiquitous. But I think that's true at both scales, at the full scale of the massing, at the scale of the elements. I just think that we now have tools that allow us to do it as designers, regardless of your background, because these tools are not replacing expertise, but they're allowing for better communication between disciplines, meaning that you don't have to be an engineer and an architect to use something like this. You just need to be able to communicate with a language that is consistent. I love that you brought the Sydney Opera House example, because that was an example of an architect who designed something without performance in mind. And then because of fabrication constraints, they redesigned it so that every shell of the Sydney Opera House had the same radius, which was not what your son wanted, but that was all enabled by computer-aided design tools that had just come out at that point. So that was performance and fabrication playing a role in the design of a really phenomenal structure. So yeah, I think it's really not about one versus the other. It's that we can do both, and we should do both.
I see. Thank you so much for the answer. Yeah, I didn't know this about the Sydney Opera House at all. Yeah, so I guess we're almost kind of short on time, and I guess I have a last question kind of for both of you. So we kind of talk about material a lot, like concrete for buildings and then clay for like art making. I guess the question is like, are we kind of overthinking would there be some kind of 21st century material that will kind of make I guess in the building sense, like cemented concrete optimization obsolete? And also, I guess, some kind of material that can also be leveraged for art making. That's not clay. Is that?
So I recently went to a ceramic printing conference symposium, which was not at all my area, because these people were material scientists. They were talking about ceramics, not in the sense of clay, but as a quartz-based, silica-based material. And they use it now in their work, in their research. And I bet there are a lot of people at MIT who do that, that they use it with polymers. So that's fascinating to me. So it's not the material that I know. It doesn't have any of the material qualities that I know, but I think it has fascinating potential. For my own work, what I'm most interested in printing with more like finding natural materials that can be printed, and then maybe like being sustainable, but then also like either using seeds in that or fungi spores and mycelium or some other materials. And there is plenty of really interesting research going on with that. So it's kind of like sustainable materials, because clay is sustainable. And that's really, Mohamed, I really enjoyed that you opened with that slide of the two ceramic pots, the water pots, and then the unfinished building, because like those are just like really amazing examples of like situated objects and materials with huge significance and value. Yeah.
Yeah, that's a great point. I can't add too much to that, to be totally honest. I entered my research thinking I would work on other materials, and concrete just ended up being relevant because it's a material that people both want and is available. It's available, it's affordable, relatively speaking, and it's often pointed to as a criminal material because of its climate impact, but that's really just because it is the material we use so much more than everything else. And we haven't found materials that are as widely available and as performatively strong as concrete, where it's strong, it is fire resistant, you can design for seismic resistance, you can make it safe, you can make it last 100 years if you are doing everything carefully. And it's a material we've had around for so long. So there's a lot of momentum behind keeping concrete construction. We don't really see it slowing down. But I really hope we change that, because like Timea mentioned, geopolymers is a whole field of research that, we're finding really exciting opportunities to change and reduce our impact through subtle changes to the construction industry that are not huge. The partners we worked with in India have been developing this amazing material with EPFL in Switzerland, which is 30% reduced carbon in comparison to cement, but it's processed the same way, using the same plants, using materials that are even more accessible to developing countries. So I see that as really like the next stage, is how do we substitute ingredients without completely changing our material stream? Because if it requires so much change, there are so many more obstacles to adopting that material. So yeah, I think there's so many options, and it's really hard for me to say which one's the best, but I see like slow changes going forward, or small changes, sorry, making big changes in the end.
Thank you both for the answers. Yeah, there are like so much like dimensionality that come with like a material that like I never think I had thought about them before. But we are almost out of time, so we kind of have to stop here. And to people with more questions, please feel free to take them offline in our Discord channel. And thank you everyone for joining this colloquium. And let's thank our speakers again for this very interesting session. And we also want to thank our artist, Spencer Ashley, for making the poster for this week. And see you all next week.